Greetings, my name is Ravinder Lechumanian. Metric number is 211090981. Today I would like to show the demo of my final year project. My supervisor name is Dr. Nunajiha binti Abu Bakar. First of all, let's start with the project introduction. My project title is Power Distribution Optimization with Economic Dispatching Strategy. Here I have listed three objectives. First one is to propose an optimal system configuration for power distribution network. And second one is to investigate an economic dispatching strategy for the system configuration. Third one is to develop an optimization algorithm by minimizing the operational cost. This project uses a deterministic optimization via quadratic programming, which we call as QP, and heuristic optimization via Gray-Wolf optimization, which is GWO, to simulate a power dispatch model for thermal power plant, incorporating two strategies, which is demand response and load shifting over a 24-hour schedule, and perform sensitivity analysis on the demand variation. The main tool that I used for my project is Python. Next is about the tool description. Here I want to show an example from my final year project, which is deterministic optimization via quadratic programming, we call as QP. The tool that I used, as I mentioned before, is Python. Okay, here we can see a screenshot of my code from my final year project, which is Python libraries. The first one is NumPy, we call as VectorMath, and the second one is Skippy Optimize Minimize, we used for the solve the quadratic programming, and the last one is Matplot library, which is for visualization for the output such as graph and so on. The reason why I use the Python software is, first of all, it is free and it is an open source software, and the most efficient one is that it is high flexible for the custom constraint. So the Skippy Optimize Minimize supports the non-linear constraint, which is crucial for the simulating the real world limits like power balance, ramp up rate, and the spinning reserve. Here we can see a two screenshot of my code, which is I have listed the constraint. So here I have the equations of the constraint. So first one is the spinning reserve. From the first picture we can see the equations of the spinning reserve, ramp up and ramp down. And from the second picture, these are the constraints that I used for my final year project, which is power balance, and upper bound we call as upper limit, lower limit, spinning reserve, ramp up, and last one is ramp down. The visualization is done using the Matplot library, like I said just now, and the font that I used for my output, which is for the graph, is Times New Roman. So to ensure that the compliance with the academic formatting, and from this picture we can see that this is the code that I set for the font for my result. Let's see about the demonstration of the tool application. For the modeling part, I have used 6 thermal generators with individual cost function. So from this code that I developed, we can see that CPI equals to A plus B PI plus C PI square, which is ABC we call as a cost coefficient. This is the code for the cost function. And second one is about the limits, which is each generator have their own maximum and minimum limits. For example, from this code we can see that for generator 1, the maximum limit is 1100 and minimum limit is 250. The next figure is about the demand schedule, which is I set in my code. From here we can see that it is a demand for every 30 minutes interval over a 24 hours. So such as from this code we can see that it is from 12 to 12:30, 1 to 1:30, and it will goes on. And the third one is about the spinning reserve, which we call as a constraint. It is a dynamic and per generator reserve the requirement, which is I set from 10 to 15% of the demand. And the next is about the ramp up constraint, which is applied to control the hourly rate of the change in generator of the output, we call as a ramp up and ramp down. So this code is for the spinning reserve and ramp up and ramp down. To enhance more about my modeling, I have done a sensitivity analysis, which we call as a sensitivity testing. So this model can analyze how the generation cost and average output respond to the changes in the demand by scaling the demand curve across multiple factors. I have set from 50% to 100%. This highlights the tool flexibility of the scenario based on the planning. So from this figure, we can see this is the code for the sensitivity analysis, which is I set from 50% to 100%. The demand factor is 0.5 to 1.0. The last part is about the visualization. In my project, I have come with many results, which I has demonstrated as a graph. So from all the graph here, I want to list it apart from it. which is the first one is the power output per generator over time, and the second one is cost per time slot, and the third one is hourly demand pattern. So let's see about the first graph of the visualization, how I set to see the graph more clearly. So from this figure we can see that the plot title is the title of each graph have their own title. So according to the title, so the font size is 14, and the plot label, which is x-axis, I set as a time slot, and the y-axis I set as the power, and the font size each have their own font size to make sure the readers and the panels can see clearly. And the rotation I have set for 60. This is because since I'm using the 24 hours, so it can be clearly see it does not out of the box actually, so it will be consist and precise in the graph, so we can see that clearly. And same goes to the next upcoming graphs. All this format I set for the each of my graph. Okay, there are some tool limitation for my project from the Python software. The first one is simplified generator modeling, which is there is no emission cost, no fuel cost, and also no startup or shutdown cost. And the second limitation is about assuming all generators are always online. And the last one is about the spinning reserve is a percentage approximation only. But not least, the QP model was successfully minimized the power cost while enforcing the realistic constraint, and the code is modular and scalable for the additional strategies like demand response or load shifting. And it is also enable the visualization of real-time economic dispatch, generator load patterns, and the cost trend and constraint enforcement. So the key takeaways from my project is about the QP delivers the efficient cost minimization under realistic limits, and the ramp up or ramp down and the spinning reserve modeling enhance the system stability, and the sensitivity analysis proves that the model robustness to the demand fluctuation.